Okay, so hopefully this time we will have an audio that goes with the class. As you know, there was an issue with somehow with the recording that the audio didn't show up. So, well, what can we do? We'll do this again. Now, you've possibly already seen the notes that were associated with class, but we'll just retype everything. We're going to talk mostly about collisions. We're not going to go very deep, but we will discuss some details. The first thing we're going to do is to talk about collisions with neutrons. Now, well, two things. First, you'll notice that some typing magically appeared. That's what I'm going to be doing for the rest of this class and the rest of this course. I'm going to try to type rather than handwrite, because for reasons I cannot imagine, I've been told that my handwriting is not so clear, not so easy to read. So let me try to type, and I can take advantage of the recording by doing the typing in advance or pause my video to pass with my devices and get things typed. Now, that's a good news. The other news are not bad, but are of some importance. Why do we care about collisions with neutrals? And the reason why we do is that, well, not in all plasmas you can imagine, but in many, there are going to be neutrals around, and therefore we will have to wonder what do these neutral particles do to my plasma. Is it going to have any importance if I have any neutrals in my plasma or not? So it does happen that this may actually be quite important, and for that reason it is relevant to have some description of how collisions happen with between our particles that constitute the plasma and the neutral particles that are around or in the plasma. The way we characterize collisions is through one fundamental quantity, that is the collision frequency, that is indicated with the Greek letter nu, which has that shape there. There it is, our Greek letter nu, but that's a frequency, so of course it has the dimensions of a frequency, which, as you very well know, has the inverse of the dimensions of time, where by t here I indicate time. Well, now, what is going to be our collision frequency, and why is that the relevant quantity? Well, what we really want to know is how often the collisions enter into the behavior of any single particle, and that is determined or described by how often does that particle collide with neutrals in the system. There is going to be one of the expressions that sort of come out of nowhere that I'm going to write for that collision frequency. But that expression, let me write it first, and then we will briefly talk about it, is given by frequency. I'm going to use subscript n and s. I will tell you in a moment what they mean. Is going to be equal to n sub n cs and sigma times sigma s. That's a sigma, that's a collision cross-section, infinitesimal cross-section. Let me first say what I mean by the subscript. This is the scattering, that's what the S stands for. Collisional frequency with neutrals. In principle, there could be other collision frequencies. If you think of plasmas with dust, dust is put in the plasma as a neutral. It doesn't stay that way very long, but the first event that my dust is going to experience is capture, absorption, collisions with ions and electrons. That's not going to be given by this cross-section. It's going to be something else. C sub s is the usual average thermal velocity of my particles, some measure of the velocity of the particles. Intuitive, the faster they move, the more likely they are to hit, to come across neutral particle while they're moving. And sigma s is, again, the scattering infinitesimal cross-section for the particle. Infinitesimal, I mean that's for a single particle. Okay. There are maybe two things to notice here. One is that this collision frequency is going to become larger as the temperature goes up, because that C sub s will go up. And the density of the neutrals is going to be important. The more neutrals there are in the system, the more collisions I'm going to have. Again, as the density of the neutrals goes up, the collision frequency will also go up. Often, instead of using a collision frequency, it's more convenient to use dimensionless quantity. So let me define another quantity here. That's going to be a time scale. And I'm going to use the Greek letter tau. Okay, here I have defined my time scale. That is going to be the time scale of whatever I'm interested in. And this could be some propagation of some wave, some discharge, that runs for days, where I want to produce fusion or observe the behavior of my dust in a long-term experiment, or on a very short time scale. In other words, what's going to matter here is what are you actually interested in, and depending on what that is, you will have to decide whether your time scale is some number or some other. And then what you do is take the product tau times nu And this is going to be a dimensionless number. So now it's easy to decide if the number is big or small. We just have to decide to look at what the number is. Is this much bigger or much smaller than 1? And that is going to make a difference in how important collisions are. Okay, then if the product is much bigger than 1, we'll call it big. And that's going to mean that the system or the process I'm interested in is dominated by collisions. However, if that product is small, then the process or the system is weakly collisional, or depending on how small that number actually is, we could just call it collisionless, which is a word that my spell checker doesn't think it exists. But anyway, that was all we wanted to discuss. Now, let me remind you again that these all, oops, I did not go straight. These all apply to neutrals. And of course, neutrals are not the only particles in my system. I'm going to have more charged particles, hopefully, than neutrals. And I will want to know what happens with those. So my next question is, how do collisions between charged particles behave? What can I say about those? And in this case, rather than from a frequency, I'm going to start from cross-section, which is actually going to be called differential scattering cross-section. And let's see what that means. That's usually, oops, wrong color, sorry, indicated with, again, the usual letter sigma with a subscript C to indicate that these are Coulomb collisions. And this is going to be function of some angle. That angle, Greek letter chi, is the angle that defines the scattering of my particles. So it's the angle between the direction before and after the collision. So if chi is 180 degrees, that means my particle bounced straight back in a direction opposite to the direction it came from. If it's 90 degrees, it took a 90-degree turn, and so on. Now, a proper interpretation of this cross-section can perhaps be more easily or more informatively given in this way by looking at the product sigma times d omega. And here is how I'm going to define that, or how I mean that. That is the ratio between the number of particles scattering to an angle, the omega, this is a solid angle, divided by some beam intensity. So here I'm thinking of beam of particles all coming in with the same direction. They bounce off some other charged particles. How many of them are they going to end up in some angle d omega? That's going to be given by the differential cross-section. Okay, here it is, the ratio between the number of particles that end up in that solid angle and the number of particles that were coming in by beam intensity. That's essentially what I mean, the particle flux. Now, I'm not going to go into how do you figure this out, but it's actually far from easy, but not quite impossible. It takes a little bit of work, but that's something we could do. I'm just not going to spend the time in doing it. What determines the behavior of collisional behavior of charged particles is that differential scattering cross-section, and there is an analytic expression for that. That's given by what is called the Rutherford formula, and this one I'm going to write in a moment. It's also in our textbook. This is where I draw the line. I'm not going to type in LaTeX all the formulas. Have a little bit of patience, but those should be easy to reconstruct if there is anything that's not clear, because they're going to be in our textbook. Okay, that expression looks something like this. I'm going to have 1/4 of E squared, where E is the charge of my particle, divided by 4 pi epsilon naught times ME, I'm thinking of electrons, of course, V squared all square times 1 divided by overdid it a little bit, the sine to the 4th power of the angle chi divided by 2. Okay, here I'm thinking of collisions between electrons and electrons, and that's the expression that's in the literature that's going to tell me what the cross-section for that collision is. Now, you will notice that there is a stark difference with respect to what we had before for collisions with neutrals. In this case, the probability of colliding decreases as the temperature increases. What is actually happening is that the velocity of the particle, which is related to the temperature, remember that the temperature is an average of the kinetic energy, therefore the velocity of the particles appears in the denominator and appears to the 4th power. I got a square here and a square here. So let me write this. That is quite strong inverse dependence on the velocity of the particle. Then the next step is say, well, whatever the expression is for my differential cross-section, let me find the total cross-section. Now, what I mean by total cross-section is the total probability of my particle to do something, to take some sort of scattering. So that's going to depend in general on how many collisions is my particle going to have in the unit time. I'm not just necessarily going to be looking at one single collision, and how much is the scattering for each one of those collisions, where does my particle end up being. So how do we calculate that total cross-section? Well, we do the total integral, the sum of overall the collisions, and the sum over all the collisions, since I'm working with, remember, differential scattering cross-section, turns into an integral. So my sigma sub t is going to be the integral between 0 and pi of my differential cross-section, sigma c function of chi, times 2 pi times sine of chi in d chi, where the integral, since my sigma sub c only depends on the angle chi, I only need to integrate over chi. And of course, you immediately notice that there is something scary or bothersome about this integral. This integral depends on the sign of the angle divided by 2 to the 4th power. So that cross-section diverges for the angle going to 0. And that kind of makes sense. If I make the angle 0, even if I don't have any collisions, the probability that my particle will continue in the same direction, well, it's 100%. But somehow that doesn't quite seem to work in the way we've written the expression. Regardless, it is apparent that the large angle collisions, so sigma c differential one for large deflection, is actually going to be pretty small, or is pretty small compared to the cross-section for small deflections. So we need to figure out a way out of this problem, and here is how this works. Think of collision between two particles. If you have one particle coming in, two charged particles, remember these collisions are between charged particles, and therefore a collision, what we properly call a collision in physics, does not require physical contact. A collision with a neutral is in practice a collision with a hard sphere. My particle, well, sphere or whatever the shape of the neutral is, but my particle comes and hits, physically enters into contact with the neutral particle. For charged particles, they're going to start interacting when they're at any distance, really, because the Coulomb force goes to 0 for the limit of the distance going to infinity. Therefore, any finite distance is going to give me a finite force That's going to give me a finite deflection. And the closer the two particles are, the bigger the deflection is going to be, because the force becomes bigger, which turns into meaning that for small impact parameter, I'm going to have large deflections, which also means, similarly to what we gather from looking at the cross-section, and that collisions are going to be dominated by the collision, that expression is going to be dominated, becomes large when there is getting this, I'm not phrasing this properly, so let me work a little bit on my if the impact parameter is small, we're going to have a very large deflection. Now that's going to diverge if the impact parameter goes to 0. However, if the impact parameter is large, I'm going to have a small deflection. But it's also true that there is going to be a lot more chances to have a collision with a large impact parameter, just because the probability of having a particle to collide with at a very close distance, very small impact parameter, is going to be much lower than having a chance to collide with a particle at a much larger distance, just because the volume involved, and therefore the number of particles involved in that type of collision, is going to be so much higher for large impact parameter and small deflection angles. Still, how do we fix now, finally, this lower limit for the integral? Well, the way we fix it is by remembering what we learned about the Debye shielding. This is going to enter by reminding us that we're going to assume that particles do not get close enough they can interact on lengths that are scale lengths that are bound by the Debye length. In other words, the Debye length is going to set the limit for the lower integral. So I cannot have collisions starting from this angle 0, but I have to figure out what that angle is based on the Debye length. And we're not going to do the calculation, but that's detailed a little more in our textbook. So I'll just leave that as little hand wavy explanation of the fact that the lower limit is not actually 0, but some number that's finite, so larger than 0. So again, the particle, the charge of my particle that the incoming particle is colliding with is shielded by the Debye shielding process, and therefore particles that are farther away than a length that is related with the Debye length are not going to be able to see that charge, and therefore they're not going to get scattered. So my particle needs to get really close in order to see the deflection. And when the distance becomes small, the angle is large, so I'm not going to touch the upper limit of integration. I can still have 90 degrees or 180 degrees deflections, but I cannot have an infinitesimally small deflection because that's prohibited by the Debye shielding. I hope that all made sense. Okay, then here is what I am going to do. I'm going to replace that limit with that zero with a lower limit that is actually constrained by the Debye length. Remember, that's lambda sub d. We're almost done. All this work was for figuring out the cross-section, but we were originally reasoning in terms of frequency. So this part is going to take a lot less time. I'm going to just write the frequency of the collisions as density of the particles I'm colliding with times the velocity of my particle times sigma sub t, the cross-section for my collisions. And this is going to be proportional to 1 over v to the third power, which is itself the same depending on your units, or proportional to the temperature to the -3 hands. So that's the dependence I can expect in my system for the frequency of collisions. So you will immediately recognize that if that temperature goes up, the collision frequency goes down. So very warm plasmas are going to be essentially collisionless. Now, very warm doesn't mean anything. We will need to look at numbers, but fusion plasmas typically are in regimes where collisions can be ignored with respect to almost everything else. So for most phenomena that we are interested in fusion plasmas, collisions are not important. I'm sure you can all think of a notable exception: fusion reactions. Well, fusion reactions are collisions. They're not going to be given by this expression. And their frequency is not going to be given by this expression, because it's going to have a different sigma. That's the sigma, the cross-section for the fusion reactions, which is going to be typically a lot smaller than the cross-section for collisions. So that is one more thing we have to wrestle with, trying to work on our fusion reactors. Okay, that was all we are going to say for now about collisions. And we're now going to go back to something we started talking about earlier, which is the plasma parameter. So let's get back to the plasma parameter and see what it can do for us in what it can tell us about the plasma in some other points. Okay, here we go. I typed my title. This is what we're going to talk about. And let me put a nice, I don't know if it's nice, but I'm going to put a box around it. And this is what we're going to consider. Now, there is a way to do a little bit more calculation on this. And that's actually in our textbook, so feel free to read it and try to work it out. But all I'm going to say is that the plasma parameter needs to be large for the plasma to be treated as a fluid. And we'll come back to this, but the idea is that this is true because a fluid description of a plasma is description of the average behavior of the particles in my plasma. In other words, I'm going to look at what is going to happen on average to the number of particles I have per unit volume. That's going to be the density. So I need that average to be meaningful. If I'm looking at phenomena that happen over a certain scale length, I need to work with my averages. If I'm using the fluid description, those averages need to be well defined. So if I'm looking at a scale length where instant t equals 0, I have one particle, then I wait some time, I look again, and that particle has gone out of that volume, and then no other particles come in. So my total variation of number of particles from 1 to 0, and then maybe a little later there is 2, but I can't meaningfully take averages. On the other hand, if I have hundreds of millions of particles in my system, then in my volume of interest, then that is a lot more meaningful. But that is all we're going to say about that part. We're going to say a few more words about the Debye shielding, which we actually have already looked at, but that may not have been all that obvious. So we took the Debye length, and to calculate lambda d, we did some assumption. If you remember, we assumed something rather specific, that this ratio E phi over T was small. And of course, phi is the electrostatic potential, so this is going to be proportional to 1 over R. And indeed, we did see that our derivation and what we found was working up to a point. Up to some minimum radius. And didn't emphasize that in the derivation of the Debye shielding, but that minimum radius is proportional to the density, the plasma density, to the -1/3. So essentially, I can define a volume of R minimum cube times 4 pi over 3, and or just a minimum cube if I want a cube and not a sphere, and look how many particles do I have in there, and decide, okay, my R minimum is going to be determined by the region of space where I have at least this many particles. That's the meaning of this. And we did see in Mathematica that when we get close to the particle, we can't find the numerical solution essentially fails. But even before the numerical solution fails, actually that numerical solution fails so quickly, so soon, because I'm not being terribly careful about how I integrate it, but eventually the potential is going to diverge, so there is no solution to that differential equation. But even before that solution starts diverging, we saw that it starts deviating from the approximate solution that we use to define the Debye shielding. And here is how the whole thing went. Let me calculate my potential at a distance equal to from the particle, the test particle, equal to my R minimum. So that is going to be given. This is something that you very well know. 1/4 pi epsilon 0 times my charge divided by R minimum. Then I can substitute that into my ratio, the ratio that I have now on top of the screen. And let's see what we find. Well, we have the expression E phi over KT. That's going to be phi is 1/4 pi epsilon 0. E times C gives me E squared over R minimum. I'm going to enter in a second. I'll put the KT sub E here, and then for R minimum, I'm going to substitute and sub E to the minus 1/3. Ouch, rather the plus 1/3, because I have 1/R min. Sorry about that. Let me fix that. And when all is said and done, this is proportional to 1 over the plasma parameter to the 2/3. Okay, so what is the bottom line here? Well, what this is telling me is that our derivation of the Debye shielding requires the number of electrons or particles. We just did it with the electrons. The only electrons are moving. The number of electrons in a Debye cube or sphere needs to be much larger than 1. For this ratio, E phi over KT to be small, I need the plasma parameter to be large. And remember what the physical meaning of the plasma parameter was. So this is the number particles in a volume that's determined by my Debye line. Okay, we're almost done for today, which probably means that either I forgot something that was in the original lecture 3, or I just talked faster, and because I think we're going to be a little shorter. This lecture is going to be a little shorter than the previous version. But, well, that may be a blessing. You decide. Let's just touch on one more thing. That is the ratio between kinetic energy and potential energy. Okay, so what's good to do with our plasma parameter? Well, you see, you can see that reasonably easily. So let me write that as K over V, and let's write down the expressions for those two quantities. I'm going to have 3/2 kT for the kinetic energy, and this multiplies for the potential energy. I'm going to have E squared, and try to have a straight line. And in the denominator, I'm going to have 4 pi epsilon naught times R, where for R, I'm going to put an average sign. Those two brackets you're familiar with for sure indicate averages. And the reason why I need an average is that here I'm comparing the average kinetic energy of a particle. That's why I'm using the temperature. I'm not picking any specific single particle. I'm looking at an average. And therefore, I need to use some average for the potential energy as well. This I'm going to define as the average separation between particles. Well, I'm sure you can now see the connection. This is going to be proportional to the density in the system. So how many particles I have in a unit volume is going to be sort of the inverse. Once I take the proper power, take it to the 1/3 of the average distance between particles. So I'm not going to do too much additional work on this, but let's see, it's not, you know, not that terribly difficult. Oh, sorry, I wrote the expression for, I now notice, I not wrote the expression for the potential instead of writing the, and I forgot to take it to the -1. So that's the potential energy. I need the inverse to do my ratio. Otherwise, I would be calculating the product between the kinetic and the potential energy, and I don't know what that what that's going to give me. All right. So if we do this, let's try to do it carefully. K over V is going to be equal to 3KT times 4 pi epsilon 0 average R, all divided by, here I have 2 and E squared, and that's all. Simplifying, I get a 6 pi, then KT epsilon 0. For R, I get n to the minus 1/3 divided by E squared. And if you put all the pieces together, you find that this is actually 6 pi plasma parameters to the 2/3. So again, we see that the plasma parameter is going to tell me if my number of collisions, that's going to be lecture 4. If my kinetic energy is much larger than the potential energy or the other way around. And of course, if the plasma parameter is large, kinetic energy is going to be larger than potential energy. That is, kinetic energy dominates the behavior of the plasma. And in the opposite case, the potential energy dominates the behavior of the plasma. That may not be called that informative. Okay, what does this actually mean? So here's how we can look at this. If this is much larger than 1, plasma parameter is much larger than 1, then what I find is that my system is going to be dominated by small collisions, small angle collisions. Those small angle collisions are going to be all the collisions I have to worry about. On the other hand, if the plasma parameter is small, and again, here I have the advantage of using pure numbers, so small and large have a meaning. I can say bigger, a lot bigger than 1 is large, a lot smaller than 1 is small. Then if that is the case, I'm going to see, to find that electrostatic interactions are important. And I'm going to call this leave me some more space, a strongly coupled plasma. Now, this is actually going to be interest to many of us, because that's the regime dusty plasmas can find themselves. And when this happens, dust is going to form crystals. Some of you for sure will already be familiar with that. This is not going to happen in fusion plasma because, well, for one thing, you don't have dust, and for another one, the plasma is not strongly coupled in terms of electrostatic interaction. The opposite limit, where the small angle collisions are dominant, it means that from the point of view of a single particle, that particle is going to rarely see a large deflection. In a collision, it's going to see a lot more small deflections instead. Now, one last thing, it's actually going to be pretty interesting what what happens in between. I said if the plasma parameter is much larger than 1, then I have a weakly coupled plasma, small angle collisions are dominant. Okay, I can buy that. The opposite, if it's much less than 1, strongly coupled plasma, and what follows. What if the plasma parameter is of order 1, or a little less than 1, or a little more than 1? Then you are in some intermediate regime, and those are, not surprisingly, those are often the hardest ones to figure out what happens in there. We're not, of course, going to get into any of that in this course, but possibly some of you will encounter this in your research. And hopefully what we said today is going to give you some idea of how things go and why one thing or another is going to be large or small, and more important or less important. Okay, we're still pretty close to the 1 hour mark. I think I saved some time by typing with a pause screen. I will, since I have a little bit of time left, I will also make one last comment. You know that sometimes I will prefer to drop the Boltzmann constant, and you may want to consider that a blessing, because I know that the way I write lowercase k can be pretty obscure. So if it's not there, you have no chance of getting confused about what's that scribbled there. Okay, that is all for this class. We can start again from the original recording of lecture 4, which hopefully had all the pieces in. I haven't had the heart of looking at it yet, but if not, we'll have to do another take on that one too. And I will see you back for lecture 4.